All right, let's talk about something you do probably 100 times a day without even thinking about it. Clicking. You click a link and poof, a website appears. But if you ever really stop to wonder about the insane journey that click just took, well, today we're going to follow one. From your finger, across the world, and back again, all in less time than it takes to blink.
I mean, it really does feel like magic, doesn't it? 1 second, there's nothing. The next, a whole web page is just there. But it's not magic. It's an incredibly fast and complex dance between hardware and software. So what is actually happening in that split second? Let's break it down.
So this epic journey doesn't start in some giant futuristic data center. Nope. It starts somewhere much closer. It starts right there with you, on your device, inside your own home.
And the very first piece of this whole puzzle is called the client. That's just the fancy technical term for whatever device you're using right now. Your laptop, your phone, you name it. Every single journey on the internet starts with a client basically saying, hey, I need to see something.
Now, your phone or laptop isn't just floating out there on its own, right? It's connected to your local area network, or what we call a LAN. Honestly, the best way to picture a LAN is as your own private digital neighborhood. It's the little network that connects your laptop to your printer, your smart TV to your phone, all under one roof. So how is this little digital neighborhood of yours actually set up? Well, most home networks use what's called a star topology. Just picture it. All your devices have their own separate connection to one central point, your Wi-Fi router. And the real genius of this setup is how reliable it is. If your smart speaker's connection goes down, it doesn't drag your laptop offline with it. Every link is independent, which keeps the whole thing super simple and really robust.
Okay, so your click has made a request inside your own little network, but the website you want isn't on your printer, right? It's out there on the internet. Your request needs to leave the house. So how does it find the front door? And this is where a super important piece of gear comes in. See, that box from your internet provider has two key parts, a switch and a router. And they do totally different things. The switch, it's like a traffic cop for local deliveries, directing data between the devices inside your house. But the router? The router is the gateway. It's the bouncer at the door of your LAN, and it's the only one that knows how to connect you to the massive, sprawling world of the internet.
And just like that, our little packet of data is out the door and merging onto the biggest information highway in human history.
So your router is the on-ramp, connecting your small home LAN to a gigantic wide area network, or WAN. We're talking about networks that span entire cities, countries, even continents. And the biggest, baddest WAN of them all? Well, that's the internet itself. It's truly a global network made up of other networks.
Now, here's something that is just incredible to think about. The internet wasn't just designed to be fast or to connect people. At its very core, it was built with one principle in mind: survival. It was designed from the ground up to be resilient. So what's the secret sauce here? It's a design called a mesh topology. See, unlike the simple star layout in your house, the internet's backbone has no single center. Instead, all the core routers are connected to each other with tons and tons of redundant links. This means if one cable gets cut or one path gets too busy, your data just finds another way to get there. There's no single point of failure, which is what makes the whole system so unbelievably tough.
Okay, so you've got billions of devices made by thousands of different companies running all sorts of software. How in the world do they talk to each other so perfectly? Well, they all agree to use the same rulebook. It's called the TCP/IP model. You can just think of it as the universal language of the internet. It's what guarantees that every bit of data is addressed, sent, and put back together the right way, no matter where it came from or where it's going.
So by using that universal language and that super resilient design, our little data packet zips across the globe and it arrives.
And that destination is almost always a server. See, most of the web you use every single day, news, social media, shopping, it's all built on what's called the client-server model. It's simple. Your device, the client, asks for something, and a big, powerful, centralized computer, the server, gives it to you. It all boils down to this really simple, elegant dance. Step 1, your browser sends out that request. Step 2, the server gets it and finds the files for the web page. And step 3, the server bundles all that data up and sends it right back down that internet highway to you. That's it. That is the fundamental heartbeat of the web.
Now, even though client-server is king, it's not the only game in town. The other model is called peer-to-peer, or P2P. Here, instead of one big central server, every computer in the network is an equal. It's both a client and a server at the same time. This is the idea behind things like BitTorrent or cryptocurrencies like Bitcoin. It's way more resilient because there's no single weak spot, but man, it's also a lot more chaotic and harder to manage.
So we've been talking pretty high level. Packets, routers, servers. But let's zoom way in, like all the way down to the wire. How does a digital 1 or 0 actually move through the physical world?
It all comes down to something called encoding. You have to translate those abstract bits of data inside your computer into a real physical signal, like a specific electrical voltage on a copper cable or a very specific radio wave for your Wi-Fi. For wired connections, one of the classic solutions is called Manchester encoding, and it solves a really tricky problem: timing. I mean, if you just send a long stream of ones and zeros, how does the computer on the other end know where one bit stops and the next one starts? Well, here's the brilliant trick. Manchester encoding forces the electrical voltage to change right in the middle of every single bit. That constant transition works like a metronome, a heartbeat, embedding the clock signal right into the data itself to keep everything perfectly in sync. It's so clever. Wireless signals have it even tougher. They've got to deal with all sorts of noise and interference. To get around this, engineers came up with some amazing techniques. One is frequency hopping, which is what Bluetooth uses. It works by rapidly jumping the signal between dozens of different frequencies. Think of it like trying to have a secret conversation in a crowded room by changing corners every few seconds. The other is direct sequence, which things like GPS and early Wi-Fi used. This takes your signal and spreads it way out using a special code. It's like instead of just shouting one word across a noisy stadium, you shout a whole long sentence that you both agreed on beforehand. Even if some noise drowns out a few words, the whole message still gets through. They're both just brilliant ways to cut through the noise.
So there you have it. From a simple click in your own digital neighborhood to a wild journey across a global mesh that's built to survive, all of it governed by a universal language and carried by incredibly clever physical signals. That's the magic behind every single web page. The principles that built this system have created the world we live in today. So it